Hi. Good, my pen works. All right, so moving on. Learning targets. Differentiate between acids and bases. Identify acids, bases, and their conjugates, conjugate acid-base pair. Relate hydrogen concentration to the pH scale. Can perform pH, pOH calculations, hydrogen concentration calculations as well. Strong acid, strong base titration using indicators, and set up and solve titration calculation problems using dimensional analysis. All right, so a couple of things that are relevant to acids and bases, like, did you know hydrangeas can vary from pink to blue depending on the acidity of the soil? So some plants like more acidic soils, and some change colors with them, like this particular plant. Ants release formic acid to alert their entire colony of danger. Acid rain, of course, can destroy buildings and statues. And acids are in lots of the stuff we eat and drink, soda being one, malic acids in apples. Any of your citrus stuff is going to have citric acid. Those lovely Sour Patch Kids have tartaric acid along with the citric acid in them. So we eat lots of acids. We ingest lots of acids. Of course, our stomach produces acid in the form of HCl, hydrochloric. And then, amino acids are, oops, rewind there. Amino acids are, in the body as well, and pretty much make structurally up our tissues, the muscle tissue and other things like that. So building blocks of lots of our body come from these lovely amino acids. Properties of acids. Acids contain the hydrogen ions or produce hydrogen ions. They taste sour, okay, or have a tart taste, corrosive to metals, low pH, less than 7, conducts electricity in water, and turns litmus paper red. And now over here we have our lovely hydroxide ions in the bases, or they produce hydroxide. Taste bitter or chalky, feel soapy, slippery. A lot of these are going to be your detergents. They have a higher pH, greater than 7, conduct electricity as well because they form ions just like the acids do. And we know that from the last unit where it produces ions in solution, it can conduct electricity, those electrolytes. Turning litmus paper basic blue. So here's our litmus paper. So red litmus paper with a drop of base will turn it blue. Blue litmus paper with a drop of acid will turn it red. Okay. Now, before we continue, we need to know what hydronium is. Hydronium is H3O+. So when an acid, this H+ is put into the solution, into water, it doesn't really just hang out by itself. It actually reacts with a water molecule and produces the hydronium ion. Now, H3O+ means the H+ is attached itself to the water. It has this Lewis dot structure over here. As you can see, the 3 ligands with the lone pair is going to make it a pyramidal shape. Okay? And what I want you to note, though, is if I say hydrogen, it is interchangeable with hydronium. The two are pretty much, we're just going to, if you hear hydrogen, it's hydronium. If you hear hydronium, it's hydrogen. You use them interchangeably because they mean the same thing. Every hydrogen that goes into water attaches itself to a water and it produces a hydronium, and that gives it its acid behavior. Now, water, pure water, is going to be neutral because it contains equal concentrations of the hydrogen, hydronium, whichever way you want to look at it, and the hydroxide. The example, of course, water here, and this is showing the self-ionization of water. It's in constant dynamic equilibrium. So the 2 waters reacting, producing hydronium and hydroxide, are at an equal rate as the hydroxide and the hydronium reacting to form back the 2 waters. And that's why there's equal concentrations always. And that's why this is going to be a pH of 7. Pure water is a pH of 7. And both the hydroxide and the hydronium concentrations at a pH of 7, they both equal 1 × 10⁻⁷ molar. So their concentrations are equal. Okay? Now, the Arrhenius acid-base theory, which is the most basic definition, probably learned this definition back in 8th grade or whatever, where the acid dissociates into hydrogen ions in water. And we know that the hydrogen attaches to the hydronium, but this is how we would write an Arrhenius reaction, where the aqueous just split apart into the ions, like so. Okay. The hydroxide dissociates in water as well, so producing hydroxide ions for the Arrhenius base. Now, this is a very easy, simplified definition, but it actually doesn't allow for a lot of bases that can act as bases to be considered bases, because in order to fit this definition, you have to have a hydroxide. Bases can produce hydroxide in water with not necessarily having one in their compound, and you'll see in the next acid-base theory definition how that is done. So this is the most basic one, but it leaves out a lot of compounds that we would consider to be bases simply because they do not contain a hydroxide. Bronsted-Lowry, we're talking acids are proton donors and bases are proton acceptors, donors, acceptors. And, you know, the H plus is what we call a proton. Why? Because hydrogen, when it loses an electron, that is simply all that is left. It is just one proton, because hydrogen is really, really small, remember? So proton donor, proton acceptor. Now, when we're looking here at, hold on, try to erase this. The conjugate acid-base pair deal. Now we're going to show our Bronsted-Lowry reactions where they are reacting with water. And so here's our acid reacting with our base, producing these two new species over here to the right. Now, one of the species over here on the product side is going to be the conjugate acid. One of them is going to be the conjugate base. So the species produced after the base has accepted a proton. So we know this one's the acid because it's going to donate over here. The H comes off and it attaches itself to the water. We get the hydronium. So this being the acid, the water is acting as the base here. Now over here, out of these two species, the one that accepted the proton, which was the water, is now going to be the conjugate acid. So hydronium, because it accepted the H, is now the conjugate acid. And the chloride, now no longer has the H attached, is now the conjugate base. Okay, the acids and base are always the labels on the reactant side. The conjugate pair, the conjugate acid, conjugate base pair is always going to be on the product side. And they differ by only the one proton, no more, no less. It's a stepwise reaction. Here are some examples of them. Okay, looking here, acid base, conjugate acid, conjugate base. So these examples show that this H is donating over here. This H is donating over here. This H is donating over here. Okay, you get hydronium out of all three. We know that. But what you'll notice about your conjugates, they're now missing the conjugate bases, they're now missing the hydrogen. This was once H2PO4, which is dihydrogen phosphate. It is now hydrogen phosphate. It's missing one of the H's. You have to add a negative to the charge as well because you're taking away one of its positives. So now it goes from -1 over here to -2 on the hydrogen phosphate over here on the right. Same thing with the positive here from the ammonium. It now just becomes ammonia, which is a charge of 0. So you take away one charge from when you take the H away. Down here is showing the base versus the acid one, where water is now acting as the acid instead of the base. So water is going to donate this way. Okay, water donates to ammonia, and that produces ammonium. But as you can see, what is the remnants left over of the water? Well, that happens to be a hydroxide. So that's the conjugate base in that particular version. What you need to know here is that this is showing that water is amphoteric. That's the key word. It can act as an acid or a base. It can be a proton donor. It can be a proton acceptor. I do want to point out, though, that water is not the only species that can be amphoteric. As you can see, this dihydrogen phosphate, guess what? It's also amphoteric. Because if I add a hydrogen, I'm going to get phosphoric acid. If I take away the hydrogen, you get your hydrogen phosphate with the 1H, and you add the -2 charge. So as you can see, it's following the H, okay? So one thing you'll be looking forward to doing in the quiz, I know, is determining the conjugate acid-base pairs. So keep in mind we're talking about 1H, which has a charge of +1. So you're really taking away or adding the charge. Since I'm listing the conjugate base for, like, say, HCl over here, if I take away my H, then it's going to turn into just Cl minus. So the H plus, you take that H away, but now the charge goes down by 1. Okay? So as you can see there. Here, we've already seen this one. We take away an H. It's now H2, and now you have a -1 charge because the charge was 0. Now we're going down to -1 because we've taken away one of the H's. So this is phosphoric acid, turns into dihydrogen phosphate as the conjugate base. Here we have carbonic acid. We take away an H. We end up with hydrogen carbonate with a -1 here as well. And that's going to be bicarbonate, also the name for hydrogen carbonate. Hydrogen carbonate is also amphoteric, by the way, because you can add an H or you could take away an H, and it would be also in that particular grouping of species, chemical species, that is. Now for acids, we're adding an H. So if I have SO4 -2 and I add an H to it, okay, now I take away one of the charges because I'm adding a plus to it. So -2 + 1, now it's -1 on that particular species. This is hydrogen sulfate or bisulfate. Same thing, so here you just add the H, take away or add to the charge by 1. Add to the charge by 1, whereas you're doing conjugate base, you take away from the charge by 1. I'm going to add this here, I'm going to get sulfuric acid, okay? So H2 here. Another amphoteric species, as you can see with bisulfate, but it goes from -1 to 0 because we're adding to the charge, and then nitrate, when it bonds with the acid, it's going to turn into nitric acid, which also the -1 now becomes 0 charge. So that's how you do conjugate acid-base pairs. Follow the H. So here's a couple examples, though, where water's not a part of the equation, and you were seeing other ones. So this is where the Bronsted-Lowry is able to do the proton donor, proton acceptor, and you see no hydroxide in here, so they can be considered conjugate acid, conjugate bases, and all of that. Now, you need to examine the entire reaction before you begin. Make sure that you are looking, where is the H going? I have HNO2 here, so I have nitrous acid. I have this HS minus species. Now over here, it's only nitrite. So the H is missing. That means this guy had to donate or give away its H. So in that particular case, this is the acid. That means this one's the base. Now over here, this one can receive an H or take back an H. So this is going to be your conjugate base, and this one will be your conjugate acid. So follow the H. Look for the H. Down here, looking here, once again, I noticed there's HF and just F minus. This one must be the acid. It's donating. Okay, so this H is being donated over. So this is the acid. That means this one's the base. Now over here, of course, the H can now donate back to the F. So this has got to be your conjugate acid. This one has to be your conjugate base. All right, so electrolytes, and I'm going to flip over to the PhET simulation, and I'm going to put this in your learning module as well, so you can play around with the simulation if you want to. But we talked about it last time in solutions, electrolytes, where something partially or wholly dissociates, and depending on that strength, whether or not it's going to light up the light bulb completely, that would be the strong electrolyte where it completely dissociates, or the weak electrolyte where you only have a partial dissociation. So strong acids and bases form strong electrolytes. You have 100% dissociation. So some strong acids, nitric, sulfuric, hydrochloric. There's a couple others. There's perchloric, chloric, perchloric, and hydroiodic and hydrobromic. So there's 7 strong acids, and we make the students in AP have to know those because that's the best way to tell between a strong acid and a weak acid. Now, the strong bases are going to be group 1 hydroxides like sodium hydroxide, potassium hydroxide, and so forth. There are a couple other in the alkaline earth metal group where we have calcium hydroxide and strontium hydroxide. So your heavier metals in the alkaline earth metals group are also considered to be strong. Weak acids partially dissociate, usually less than 5%. Carbonic acid, acetic acid, and one of the bases would be ammonia, where it causes a partial dissociation. What do we mean by partial dissociation? So a strong acid, everything separates into the ions. So you get equal amount of ions and it's 100%. Well, weak acid, only a few of them dissociate. So like this one and this one is the only one that broke apart. Everything else stayed together. So you have very few ions, and that's why it's a weak electrolyte and it only partially lights up the light bulb. But let's take a moment to look at the simulation real quick. All right, so you can start out with just water. You can show the solvent, okay? Strong acid where you see everything's broken up. A weak acid where these little gray ones, they're staying together, whereas the other ones are separating into the conjugate and the hydronium, where the H plus has attached itself to the water. So as you can see in the reaction down here. Now, this simulation is good because you can look at pH paper. The color key down here is like acidic. Of course, 14 is basic. You can use the light bulb, stick that in there. Partially lights up, but if we go to the strong acid, look, it's lighting up a lot. So you can use that, or you can use the pH meter, dip that in there. But if we're looking at the weak one, the weak's be a little bit higher in terms of that. Now you can also use this part of the simulation where you adjust the concentration, okay? Weak, strong, okay? So all dissociated versus just a few dissociated. You can move this bar around too. But this is just something that you can play around with to get down that particulate model example. And the little, ones with the 3, those are the hydronium. The blue ones are the conjugate base. Okay, so take a look here. And this double arrow means that, yes, it's an equilibrium position for weak acids and bases. Whereas if we're looking at strong, it's a completion arrow going towards the products. So weak ones, you have an equilibrium position. We'll discuss more what an equilibrium position is next week, but basically you have a certain amount that is staying as the reactants, a certain amount that's becoming the product, and it's not going to completion. So the rates are equal. pH, value to express the acidity or alkalinity of a solution, how acidic or basic it is. pH means power of hydrogen. So when we're talking pH, we're talking about hydrogen concentrations and comparing it to hydrogen concentrations. So the higher the hydrogen concentration, the lower the pH. So down here by 0, you have a higher concentration, 10 to the minus 1, of hydrogen. When we are closer to the basic, where it's a pH of 14, look at that, 10 to the minus 14. That's a very low number of hydrogen in there. Yes, you have a higher concentration of hydroxide when we get down to the bases here. Of course, we said 7 is neutral. So going further away from 7 is going to be becoming stronger. Going towards 14, you're a stronger base. Going towards 0 is going to be a stronger acid. So some things to, here are just household products that show you different things on the pH scale, like pure water, soft drink, black coffee, lemon juice down here too. Ooh, that stuff's pretty potent. But like soapy water, ammonia, bleaches, these are all the detergents and oven cleaner stuff, and that's why they taste really bitter. We don't usually eat a whole lot of bases, but we have a lot of acidic food and drink types that we can, ingest and that we like, because it has that tart, sour taste to it. Now, pH, a measure of the hydrogen concentration. pOH is a measure of the hydroxide. Now, we don't really use this as a gauge measurement, but we need it in calculations sometimes. The one thing you have to know is that pH is a log-based scale. So, and it's a log-based 10 scale, I should say, because every unit change in the pH is a factor of 10 change in the concentration. Okay, so keep that in mind. So these are our equations, the main ones at least that we use. where, you know, what we're saying here is like a pH equal to 1, the concentration is 1 times 10 to the minus 1, or 0.10 molar. A pH of 2, though, okay, is going to be 1 times 10 to the minus 2, which is 0.01 molar. So as you can see, it's a factor of 10 between them to go one entire number on the pH scale. Now, you're going to need to use your log button. And so there's the log button, and then there's the 10 to the x button. These are on your calculator. You're going to need to be able to use those. And you're going to need to be able to reverse the equation. So I'm going to show you the reversed equation as well. So pH equals negative log of the hydrogen concentration, whereas pOH equals the negative log of hydroxide. But pH and pOH add together to equal 14. Okay, so keep that in mind. All right, one other thing to point out before we get into the calculating part is the concentrations. Okay, so we're at pH of 7 here, neutral. And as you can see, you know, remember hydronium is the same thing as hydrogen. Okay, at that pH of 7, the hydroxide and the hydronium are equal. Okay, but as you get closer to 0, the hydrogen or hydronium gets larger in concentration and increases in concentration, whereas the hydroxide increases in concentration as you get closer here to 14. All right, so more common household things, just to point out, you know, a few on here. Milk. A lot of people think milk is basic, but it's actually slightly acidic. And, you know, once again, all the household detergents and stuff are usually on the basic side. You know, orange juice, vinegar, cola, lemon juice. Okay, lots of these are going to be into that acidic range here. Okay. Here are the equations, and I also put this in the document that's going to be your practice so that you'll have them right in front of you. So this one right here I already introduced to you. The pH plus the pOH gives you 14. The pH equals the negative log of hydrogen. The pOH equals the negative log of hydroxide. Well, what is really this then? This is the hydrogen concentration times the hydroxide concentration gives you this 1 times 10 to the minus 14. So it's really just the values without the negative log in there. Here, to undo the negative log of hydrogen, basically you have to do 10 to the negative pH. So you're reversing it, and that's where I said you're going to need that 10 to the x button and the log button. Now, in order to get 10 to the x on those graphing calculators, you have to do second first, and then you hit it, and you'll get the 10 to the x button. This chart is very nice and helpful. It's a flow chart. So you can follow the arrows to figure out how to figure out, you know, like if I'm starting here at hydrogen and I want to know the pOH, I have two ways I can go about it. I can do the negative log of the hydrogen concentration, use this equation and get my pH. Then I can subtract my pH from 14 to get the pOH, and I can go this way. Or if I want to go the other route, I can use this top equation. The hydrogen times hydroxide concentration gives you 1 times 10 to the minus 14. That will get me over here to the concentration of hydroxide. And then I can do the negative log of the hydroxide and get pOH. So if you follow the arrows, it tells you which equations to use. But basically, you can either use the list form or you can use this to help you remember how to calculate as you're doing the problems. So what's an example of a problem? This one's very simple. With a hydrogen ion concentration of 1 times 10 to the minus 4, what is its pH? So you just get out your equation, insert your number here into the hydrogen concentration, and you calculate. And what you'll notice, if it's 1 times 10 to the minus 4, the number in the exponent here is actually the pH. What is the hydrogen ion concentration with a solution of a pH of 6? This is where we're going to undo this equation and do the 10 to the x form, this version. Okay, so now we do 10 to the minus 6. Okay, 10 to the minus 6, and then we get our hydrogen concentration is 1 times 10 to the minus 6 molar. So here, what is the pH and the pOH of this hydroxide, this sodium hydroxide? So we're going to do, in this case, decide to do negative log of the hydroxide concentration. And we get the POH is 8. Now you can do the pH plus POH gives you 14, subtract, 14 minus 8, and that's going to give you a pH of 6. Last but not least, this is one without the normal whole numbers where we're dealing with a random number, and you're going to get some of those in your practice as well. What is the hydrogen ion concentration? Well, we've got to undo it and do the 10 to the x form, 10 to the negative pH. So stick in that negative 0.35 into your calculator, and you're going to get the hydrogen concentration. So here, this has, we're going to say this has 3 sig figs, so we keep 3 in our concentration. So it was rounded to 4.47 times 10 to the minus 7. And that makes sense because it's close to a pH of 7. So the concentration should also be kind of close to that 1 times 10 to the minus 7. All right, acid-base titration here. So you're going to have to do a simulated titration online. Now, what you're going to see here is it's going to follow the neutralization reaction, okay? Where we have the base plus the acid gives us the salt and water. All right, as you can see here, we're also going to use some tools over here. This is called the burette, and it's spelled both ways. You can spell it like that, or you can spell it with the 5 letters. It doesn't matter. But it's kind of a reverse graduated cylinder. The markings go in the reverse direction. If you remember what a graduated cylinder is, it goes upright. But we're still measuring from the bottom of the meniscus here. So this is 39.1, 39.2, 39.3. And then we estimate that last digit, and it's just slightly above that 39.3. So we get our correct measurement. Now, you're going to add, using the stopcock here, you're going to add some of the fluid in here and the solution into the flask to neutralize. And as you add it, then you mark, where you stop, and that volume that was added will be used in the calculations later. In the flask is usually going to be an indicator along with one of the solutions. Most of the time you put the unknown solution in the flask and the known one, the one that the concentration. So the known one, that one's known as the titrant, and it usually goes in the burette. It doesn't always have to. The unknown concentration, that's going to be the analyte. Okay, and that's usually what we're trying to figure out is the unknown, either its volume or its concentration in our calculations. It produces this weird curve called a titration curve. And what you'll notice is this is a strong acid titrated with a strong base. So you start down here at a lower pH, and as you add it, you finally reach something called the equivalence point. And that is where the moles of the hydroxide equals the moles of the hydrogen or hydronium. And that pH right there value at the equivalence point, the volume added, moles equal the moles, okay? So keep that in mind. This is going to look like this S-shaped curve if it's an acid with the base, okay? And then you can figure out the volume needed to reach that equivalence point. This particular one is showing you starting with a strong base being titrated by a strong acid. So you're starting up here in the higher pHs, obviously still reaching that equivalence point where the moles equal the moles. Moles of OH equal the moles of the H+, okay? And we can use that amount to figure out information about our analyte. And of course, you'll have that measurement, but it's the reverse curve, but it still has this long inflection point here, this inflection point going down, okay? And you put an indicator in there to change colors when you reach that equivalence point. So what do indicators do? Well, indicators change color and at certain pHs. Now, we're going to be looking at the bromothymol blue one and the phenolphthalein. Those ones are typical ones that we use in the lab. What happens when the indicator changes color, we call that the end point. The end point and the equivalence point are not exactly the same thing. The equivalence point is when the moles equal the moles. The end point is when the indicator changes color. Now you want them to match. You want it to change color when you reach the equivalence point. So if I know that my pH at my equivalence point is going to be around 7, I'm certainly not going to pick methyl violet as my indicator because that one changes color at about a pH of 0.8, not even close to 7. I need to pick one that's close to 7. And the titrations you're going to be doing are strong, so their pH change will be around 7. So you would end up picking that. Now the ones in the simulation are bromothymol blue and the phenolphthalein, so that's why I'm picking those ones out for you. Now the end point is when it changes color. The equivalence point is when the moles equal the moles. That's the stoichiometric point. So realize that equivalence and endpoint do not mean the same thing. They should be, like you should pick an indicator that's endpoint is going to be close to your equivalence point though, or you won't get valid data. So phenolphthalein turns pink when it's basic. So this is the basic form, and the acid form is just clear. Bromothymol blue has 3 colors. It's acid, it's yellow, base, it's blue, and then right around 7, it does turn green. It turns green for just a moment. Oh, so now on to titrate calculations. And you're going to use dimensional analysis in order to solve these because you need to do some stoichiometry. What you need to see in this particular reaction is we've got sodium hydroxide and hydrochloric acid. Now this is a 1-to-1 relationship here. So 30 milliliters of 0.1 molar sodium hydroxide neutralized with 25 milliliters hydrochloric. Determine the concentration of the hydrochloric. So we're going to set this up and we're going to use some things like 0.1. This is going to be moles over 1 liter. We get to use this as a conversion factor for our sodium hydroxide, by the way. Okay, so we're going to be using that in our T-chart and being able to flip it if needed. So we first take our 30 milliliters. We want to change that to liters, so divide it by 1,000, put that in the chart. Or you can just start it off at this if you want to. Begin with your chart. You don't have to do this extra step. Now we're going to go from the liters to the moles using this as our conversion factor. So 0.10 moles equals 1 liter right here. That's where we're inserting it there. Now I can do my mole ratio. 1 mole of sodium hydroxide to 1 mole of acid. So stick in that mole ratio here. That goes there. That's the stoichiometry part. And we want volume, no, we want concentration, sorry, concentration of our acid here. So we need to divide it by the liters. So we put the volume on the bottom, but we can't use milliliters. So guess what we're going to do? Change it to liters. So divide that by 1,000 and change that to liters. Now you can cancel. Everything will cancel. Milliliters, milliliters, liters, liters, moles of NaOH, moles of NaOH. Now we're left with moles of the hydrochloric, and we're left with our liters of hydrochloric. So this could be written also as moles per liter hydrochloric, or you can write it as 0.12 molar with the big M like that. Either way it works. So this is an example where it's 1-to-1. Let's look at this example where it's not 1-to-1. We have nitric acid and we have calcium hydroxide. So we have 2 hydroxides for every 1 H. So this one we have to balance, and if you're predicting products, you know that H goes with the OH to produce water. The nitrate goes with the calcium, and calcium's a +2, so +2 in the nitrate, which is a -1. We end up with, 2 nitrates there. Now in order to balance this though, let's change this to HOH. We have 2 hydroxide groups, so we're going to need a 2 here. And because of that, our H groups now need a 2, so we're going to put a 2 there. So what you notice here, this is a 2-to-1 ratio. 2 of the acid to 1 of the base. Okay, so when we set up our T-chart, we need to make sure we do the right stoichiometry here. So how much of the 0.5 is needed to neutralize 25 of 0.05? So I'm going to start with this guy because we know everything about it. So start off with your volume. Once again, you can start off changing it directly to liters first if you want to. You don't have to do this step, but you can. You can also incorporate it in. Now, this is the going to the molarity here. Remember, this is moles over 1 liter. So we can use this as the conversion factor and flip it. So the liters go on the bottom, the moles go on the top, the 0.05, 1 liter. Okay, putting that in there as the conversion factor. Now, we have the moles of calcium going to the moles of the acid. So 1 mole of calcium, 2 moles of acid. Now, I have the molarity of the acid rather than the volume. So remember, this is moles over 1 liter. But what do I diagonal down? The moles need to go down there. So the moles go on the bottom, the liters go on the top. That means the 0.5 is going to go on the bottom and the 1 is going to go on the top. Now, as you can see, everything will be able to cancel. And what we have left is just liters of the acid, the nitric acid. And this has 2 sig figs, this has 3, this has 2, so we're going to keep 2 in our answer. The last example here is showing you another one where we have 2 hydroxides, but now we have 2 H's in our acid. This is sulfuric. So when we set up our reaction, guess what? It goes back to being 1-to-1 at that point. So 1 of the calcium hydroxide is going to neutralize 1 of the sulfuric acids. Because there's 2 H's here and there's 2 hydroxides here. That produces 2 moles of water in that process. So setting this up, like I said, already taking this and turning it into liters is fine. Divide it by 1,000. Go ahead and do that. We're going to use this as the conversion factor here. 1.5 moles of calcium hydroxide equals 1 liter of calcium hydroxide. Then it's 1-to-1 here, our mole ratio, 1-to-1. So that's what we're putting in here in our mole ratio. And then we're going to use this molarity, 2 moles per 1 liter of the sulfuric acid. But the moles diagonal down, so the 2 goes on the bottom, the 1 liter goes on the top this time. Very similar to the previous problem. So once again, this has 3 sig figs, 2 sig figs, and 2 sig figs. So we're going to make our answer have 2 sig figs.